Good afternoon, lads and ladies. Looks like we're still missing a few folks. Let me check my watch. It might be a bit early, but I don't want to. No, we're right on time. I don't want to waste any time today because today is it's a big, exciting day. Today we're actually going to play with some matrices. So let's get to that just as quickly as you can. Before we get started, I do want to let you know, and I sort of apologize. I haven't yet finished grading your exams. Almost done. I think most of you here, your exams have been graded, but some of them have not been. So I'm working on it now, and I'll have them done today, as always. The rule's a week. I'd like to have it done, before class started. But I promise the grades will be in today. I'm working on it as we speak. It's just been a busy week. So, without further ado, here we go. Last week, we did a sort of quick and dirty introduction to systems of linear equations, looking at 2x2 systems and then 3x3 systems, with the understanding that they generalize from there. The methods are the same. The big take-home lesson from last week, I have a few things. Elimination, no substitution, elimination. You eliminate and then back substitute. There's no reason to ever try and solve a 3x3 or 4x4 system by elimination. Or a larger system, certainly, unless for some reason it's like really easy to do so. Like, the equations are super simple, like you've just got one or two variables and most of the coefficients are 0, something like that. So this is MAC1140, which is pre-calculus. It's a lecture, and today is August 2nd, 2021. So we are getting perilously close to the end of the course. This Thursday is the last day of class here. And right now our plan is to have exam 3, the last midterm exam, in class this Thursday. If I need it, I may give you a take-home instead of doing the exam in class. If I need that day for lecture, I may do that because I don't like the idea of rushing things here. There's a few topics at the end that are important, like matrices and matrix algebra. It's important stuff. So are the sequence and series things. Well, I think we probably can get through it today, tomorrow, and Wednesday. It would probably feel a little more comfy. So, little announcement. Exam 3, which is currently scheduled for, just make sure I'm not crazy. This week is our last week of class, right? I'm pretty sure it is. Currently is scheduled for, 8/5. May be given as a take home. That way we can use that day for lecture. And you're not being tested on stuff that you just learned that week in a high pressure test. I think I like that more. In fact, will be given as a take home. All right, so rather than doing a proctored test in class that day, at the end of the day on Thursday, I will post a PDF of exam 3 for you, which you will print out. There'll be a little honor pledge at the top that you have to sign. Your work must be your own, and you'll be scrutinizing it very carefully. Print it out, fill it out, solve it like worksheets. Being reasonable, not using your textbook, not Googling things, just your notes. You're free to use your notes on that. And then scan and submit. So that's what we'll do. I think that takes a little bit of the pressure off of you and allows us to go a little more reasonably through the remaining bits of material. Today, we're going to talk about matrices and matrix algebra. These are sections 10.3 and 10.4 respectively. So matrices are kind of a very natural thing to start talking about after talking about systems of linear equations, because after you solve a bunch of systems of linear equations, you guys are probably feeling this in the homework now, you start to realize it's really just the numbers in front of the variables that matter. there's no real reason to keep writing the variables if you allow the physical space to keep track of the variables. So that's the idea. That's the idea. So the big idea is in a system of linear equations by let's grab a system here. 3x minus 2y plus z equals 5, x plus 3y minus z equals 0, and minus x plus 4z equals 11, we could skip writing variables. Just remembering that everything in the first column here is x's. So the first column I would write 3, 1, negative 1. Everything in the second column is y's, and this blank space here would be a 0y. So I'd write negative 2, 3, 0. And remembering that everything in the third column is z. So I'd write 1, negative 1, 4. Skip writing the variables and let the location of the numbers kind of keep track. So that matrix, well, let me, rather than going in and writing the matrix for this, that's the big idea of a matrix. So I will do it. So rather than writing this system, 3x minus 2y plus z equals 5x plus 3y minus z equals 0, negative x, I'm going to write that plus 0y plus 4z equals 11, I would write the following rectangular array of numbers. 3, negative 2, 1, 5, right? All the numbers from my first row, just without any of the variables. Then in the second row, I'd write 1, 3, negative 1, 0. And then in the third row, I would write negative 1, 0, positive 4, and 11. And your book uses a square bracket. I like these rounded parentheses instead. You put big brackets around them. You could, like I said, instead of these big parentheses, you could put angular brackets here if you wanted. And to remind ourselves where the equal sign goes, I like to put a little dotted line here. So this thing on the right is what's called the augmented coefficient matrix for this system. And all the row operations that we were doing with these systems, like multiply row 1 by negative 2 and add it to row 3 or whatever, you can do that with this. All the same shit works. It's just saving you some writing, which, you know, I imagine if your hands are like mine, getting calloused and sore from all the writing you do, you'll appreciate that. It gets better though, because there's an algebra of these matrices. Like you can multiply two matrices, you can add, subtract two matrices. Dividing matrices is a little complicated. And that's going to be one of the big things that we kind of approach, is the closest thing to the concept of dividing a matrix. So if it's okay with you, now that we kind of understand what a matrix is, I'll define it formally, and we'll look at where the things in that definition come from. You know, all the X stuff is in column 1, all the Y stuff is in column 2, all the Z stuff is in column 3, and your right-hand sides are on column 4. Now, matrices are studied outside the context of systems of equations. So a matrix is something that I care about very much, even if I'm not talking about a system of equations. We have a more general definition, a matrix, and we like to give things names in mathematics. So a matrix A, actually, I'm sorry, and n by n, or n by, let's say m by n, matrix A is a rectangular array of numbers. Whose entries can correspond to the coefficients of a system of linear equations. Now, what do I mean when I say m by n? Well, that means that there's going to be m rows. This is the number of rows, and n columns. This is the number of columns. So the matrix, the kind of general matrix A that I'm describing in this definition would look like this. We use subscripts to keep track of which entry goes in which spot. So the very top left entry, I would call A11. And then the next guy, I would call A12. And then the next guy, I would call A13. And I go all the way until I get to the last entry of the first row. Since there's supposed to be n columns, this would be A1n. So the subscripts correspond to the location within the matrix of that entry. So here, this would be the 1-1 entry. This would be the 1-2 entry. This would be the 1n entry because I've got n columns. The second row would look like this. A21, A22, out to A2n. And we'd keep going until we get to a M1, a M2, to a Mn. So this would be an M by N matrix. And each one of the little A's is an entry. The subscript indicates its location. So the first guy there tells you what row you're in. This guy is in row 1. And the second guy tells you what column you're in. This is in column 2. So the entry A32 would be come down to the third row and over to the second column. Turns out, very useful notation. Very useful notation. All right. So that's what a matrix is. We call this the dimension. M by N is the dimension of the matrix A. And the entries are A, I, J. Right? This indicates the row I and column J. Right? That's what a matrix is. And you've already seen up here how a matrix can come from a linear system. The particular kind of matrix we're looking at here, remember, is what's called the augmented coefficient matrix. The coefficient matrix would just be these guys. the 3 by 3 submatrix whose entries are the coefficients from the system. And then the stuff on the right-hand side over here, this is why we call it augmented, because you kind of augment or slap on, include the numbers from the right-hand side. So let's look at an even simpler example. e.g., for example, let's write the augmented matrix for the system. Can only do this for linear systems, by the way. Nonlinear systems don't have the kind of standard form that linear systems do. So if I have 2x minus y equals 5, and x plus 4y equals 7, this guy I can rewrite in matrix form as 2 from this guy, -1 from this guy, 5 from this guy, and then my second row would be 1 from this guy. This guy tells me to put a 4 in the y column, and this guy tells me to put a 7 on the far right-hand side. And I'll put my little dotted thing in here, and my brackets or parentheses, whatever you like out there. You can use either one. Your textbook does not include this dotted line, and I think it's quite likely that WebAssign might not include this dotted line on the homework problems, but I recommend that you keep track of it like that. It just makes life easier. And the good news is, right, that you can do all the row operations that you want to do. All 3 elementary row operations on matrices, just like linear systems. So if I wanted to solve this system right here, I can begin with my matrix 2, -1, 5, 1, 4, 7, and start running it through that solution algorithm that we had last time, the row reduction algorithm. Our goal is to get the matrix into upper triangular form now, rather than getting the system into upper triangular form. That's the idea. So the same row operations, we can do those here. Remember, the first thing you want to do is make the pivot position, the guy up here, a 1x. And one of your row operations is to just swap 2 rows. So rather than working hard to make this 2 into a 1, I can just swap row 1 and row 2. So here's the notation I would use for that. Row 1 and row 2 are going to swap. So that's going to become 1, 4, 7, 2, -1, 5. And now I want to kill the 2 down here. So I would say that my new row 2 is going to be my old row 2 minus 2 copies of my old row 1. So row 1 won't change. 1, 4, 7. 2 times -2 times this plus this is 0. -2 times this is -8 plus this is -9. -2 times this is -14. -14 plus +5 is -9. And what you see is that now this is in upper triangular form. I could go even one step further if I wanted and divide through row 2 by -9. Let's do that. So my new row 2 is going to be -1/9 times my old row 2. So row 1 stays 1, 4, 7. Row 2 then becomes 0, 1, 1. And this is even better. So now this is definitely upper triangular. Everything below the main diagonal is 1. There's just that one entry down there. And if you want to solve the system now, you just rewrite it as a system and back substitute. So that would be x plus 4y equals 7 and 0x plus 1y equals 1. And you know, back sub y equals 1. First equation, you get x plus 4 equals 7, which tells me that x is equal to 3. So there you go. Your solution is the ordered pair 3, 1. And for larger matrices, larger systems, bigger than 2 by 2, writing them as matrices like this is very, very nice because it just saves you a lot of writing. It's also going to allow us to abstract, to go from thinking about these things as systems of equations, and, you know, we've got many equations and many variables, to thinking about it as a single matrix equation. I will lead you there gently. But the first thing you need to remember is that all 3 elementary row operations from before are still kosher. So you got to remember what those elementary row operations were. You can add a multiple, a non-zero multiple. Of one row to another. You can multiply a row by any non-zero constant. And you can swap 2 rows. Those are the 3 things that we were allowed to do to systems. Those same 3 things we are allowed to do to matrices. Of course we can, because the matrix is just, it's the same thing as the system. It's just, you know, we're not writing letters anymore. Remember the sort of general algorithm for solving the system was to get it into that upper triangular form. That has a slightly different version in the matrix language called row echelon form. And then there's something else called reduced row echelon form. So I'm going to give you a little bit of vocabulary. For matrices. So when I say I'm going to put a matrix into row echelon form, this means that the first non-zero entry in each row is 1. Right? So here, if you look at your first row, its first non-zero entry is 1. And if you look at this row, coming from left to right, its first non-zero entry is 1. I should say it like this, row echelon form. This is the first non-zero entry each row is 1. The way your book says the next term is that the leading entry in each row is to the right of the leading entry in the row above it. I don't like that way of saying it. So the next two conditions I'm just going to say are the matrix is upper triangular in the sense that we talked about with systems. So row echelon form, what does that look like? That's like 1, 7, -3, 2, 0, 1, 6, 0, 0, 0, 1, 3, 0, 0, 0, 1. Something like this. This is row echelon form. This is a 4x4 matrix in row echelon form. All this stuff needs to be 0. Everything below the main diagonal is 0. And everything on the main diagonal or the first, I'll say it the way here they do, the first non-zero entry in each row is 1. So I could make this a little bit different. Like I could have this be, the second row, for example, could be 0, 0, 1, 6. And then this one could be 0, 0, 0, 1. And this could be all zeros. That would also be row echelon form. There is a further way to do this. I guess one other thing I should say is that any row with all zeros should be at the bottom. Reduced row echelon form means that in addition to having everything below the main diagonal be 0, you also have everything above the main diagonal 0. But you can see how being in this row echelon form corresponds to your system being in triangular form. It's the easy form to solve. It's just that in addition to that, we require these to all be 1s. And that means that this last equation here would just have like, let's say this last equation here, the equation that corresponds to that row would be like z equals 3. If this was an augmented matrix, this would be 0x plus 0y plus 1z equals 3. And it's nice to have it like that, just like we saw here, because then you don't even need to divide over by a constant to get your last variable. You just read it off. So some other examples of things that are in row echelon form. Here's a big matrix that's in row echelon form. 1, 3, -6, 10, 0, 0, 0, 1, 4, -3, 0, 0, 0, 1, 1/2, and a row of all zeros. 0, 0, 0, 0. This is in row echelon form. All right, so you see, it's not necessarily that the main diagonal is all 1s. It's just that the first non-zero entry in each row is a 1, and that everything beneath that first entry in each row is zeros. So that's the idea. In other words, you're kind of trying to get all the non-zero stuff up into the top right and everything down in the bottom left to be zeros. Another example, I'll call this the matrix A. Next example, I'll call the matrix B. This one is going to be in reduced row echelon form. We'll call this guy 1, 3, 0, 0, 0, 0, 0, 1, 0, -2, 0, 0, 0, 1, and then, how about 1/3? And then all zeros, 0, 0. Now this matrix here, B, this is in reduced row echelon form. Because you see, if you look one column at a time, we've got a 1 here. So first, got to be in row echelon form. So look one row at a time. The first row, his first non-zero entry is a 1. The second row, his first non-zero entry is a 1. Third row, his first non-zero entry is a 1. The last row doesn't have any non-zero entries, so he's allowed to have that as long as it's the last row. Then you look one column at a time. In the first column, everything beneath the 1 is 0. In the second column, I don't have anything interesting here. I don't have anything there, so I'm not worried about it, but I need these to all be 0 as well. If you look in the third column, so corresponding again to the second row, the first entry is a non-zero entry, is right here, and above him and below him are zeros. In the third row, fourth column, this guy above him and below him are zeros. The reduced row echelon form is sort of the absolute easiest way to see the solution of the system. But row echelon form is fine. Reduced row echelon form doesn't hurt. Just some terminology. I'm not going to beat you guys to death with this. I'm just going to tell you that the goal is to use those row operations to get your matrix into row echelon form. And the way you do that is using the row operations. So kind of the meta here. If I give you a system of equations that I want you to solve, write the matrix, use that same procedure from last time where you make the pivots 1 and clear out everything below in each column to get it into row echelon form. If it's easy or you want to, you can put it into reduced row echelon form. By then, using this row, say I've got this row here, but above him are not zeros, then I could, just like I use this guy as a tool to clear out everything below him, I could use this guy as a tool to clear out everything above him. But generally, you give yourself more work to do that way. So I don't recommend it necessarily. Let's try one of these. Let's go ahead and try to actually solve a system of equations using matrix methods. So here. So example. So here's my system. 4x plus 8y minus 4z is equal to 4. 3x plus 8y plus 5z is equal to -11. And -2x plus y plus 12z is equal to -17. So I would start by writing the corresponding matrix, which would be 4, 8, -4, 4, 3, 8, 5, -11, -2, 1, 12, negative 17, and I like to put my, maybe I won't dot it, I'll just draw it as a solid line to save time. All right, there's our matrix. I want to use row operations to get this into row echelon form, at least my upper triangular form. First step, look at row 1. If this isn't a 1, make it a 1. Is there an easy row I can swap it with to make it a 1? No. Can I easily divide through this row by 4 or multiply by 1/4 to make it a 1? Yeah. And in doing so, I won't even introduce any fractions. That's nice. So my new row 1 is going to be 1/4 times my old row 1. So rows 2 and 3 don't change. 3, 8, 5, negative 11. Negative 2, 1, 12, negative 17. And then if I multiply that by 1/4, 4 times 1/4 is 1. 8 times 1/4 is 2. Negative 4 times 1/4 is negative 1. And 4 times 1/4 is positive 1. So yeah, maybe I'll use the dollar. No, it doesn't matter. Okay, now that this first pivot is a 1, I use him as a tool to clear out everything below. So to kill this 3, I will multiply row 1 by negative 3 and add to row 2. So my new row 2 is going to be my old row 2 minus 3 times my old row 1. So row 1 definitely not changing. 1, 2, negative 1, 1. Negative 3 times this plus this is 0, and we do write the zeros in matrices. Negative 3 times this is negative 6 plus 8. Negative 6 plus 8 is positive 2. Negative 3 times this is positive 3 plus 5 is positive 8. Negative 3 times this is negative 3 plus negative 11 is negative 14. And I'm going to actually sneak in a second row operation in this one step. I know I need to kill the negative 2 down here. So I'm going to multiply row 1 by positive 2 and add it to row 3, because positive 2 times this plus this is 0. So in addition to that, I'm going to do my new row 3 is my old row 3 plus 2 times my old row 1. So 2 times this plus this is 0. 2 times this is 4 plus this is 5. 2 times this is negative 2 plus 12 is positive 10. 2 times this is positive 2 plus negative 17 is negative 15. Doing 2 row operations at once is a little dangerous, because if you make a mistake in your arithmetic, it'll be harder to catch. You're going to have to be looking for more than one thing. But you know, it certainly is possible. That's what it looks like. What would my next step be if I want to move towards getting this into row echelon form?
You need to get rid of the y in the third row.
It's true, like the y in the third row, which is represented here by this 5, right? That's like a 5y. I want to kill that. Before I do that, what do I want to do? Something with the second row.
Set the second y to 1.
Yeah, I'd like to get this 2 to be a 1. I want my pivot in column 2 to be a 1. So I can multiply through this second row by 1/2. Row 2 is going to be 1/2 times my old row 2. Rows 1 and 3 won't change here. I'm not going to try to sneak an extra one in on you again, not this time. Again, we're lucky in that all these numbers are divisible by 2. If not, we'd have fractions. We'd deal with that. Okay. Now we're ready to go ahead and kill that 5 in column 2. So to do that, I will multiply this row by -5 and add it to this row. In other words, my new row 3 is my old row 3 minus 5 copies of my old row 2. Rows 1 and 2 aren't changing here. Zero times -5 plus 0 is still 0. 1 times -5 plus 5 is now 0. -5 times 4 is -20. -20 plus +10 is -10. -5 times -7 is +35. +35 plus -15 is, what's that? Negative, +35, -15, +20. So now I've got a 1 in the pivot in the first column and zeros below, a 1 in the pivot of the second column and zeros below. Next, I'd want a 1 here. So I can divide through row 3 by -10. Multiply by -1/10. And that will get me into row echelon form. So 1, 2, -1, 1, 0, 1, 4, -7, 0, 0, 1, -2. And I guess I stopped writing my augmentation line. I should put that in, right? Again, your book and homework don't necessarily write the augmentation line, but I think it's helpful. All right. If I wanted to solve the system at this point, I could easily do that. From this last row, I can read off z equals -2. And this guy says y plus 4z equals -7. This guy says 1x plus 2y minus 1z equals 1. So we can go ahead and rewrite this as a system and solve that, which will be an upper triangular system, x plus 2y minus z equals 1, y plus 4z equals -7, z equals -2. There's your new system. This is what we call a sparse system, right? Missing a lot of stuff. And that's nice. We like sparse systems because they're easy. Z is -2. So since z equals -2, equation 2 says y plus 4 times -2 equals -7. In other words, y minus 8 equals -7, so y has to be 1. We've got our z, got our y, and now we can substitute both of those into equation 1. So say x plus 2y, x plus 2 times 1, minus z, so minus -2, is equal to 1, which really says x plus 2 equals 1, x plus 4 equals 1. So x would be 1 minus 4, which is -3, i.e. our solution is the ordered triple -3. So when we teach systems in college algebra students are terrified of 3x3 systems for several reasons. One, because they always want to try to use substitution rather than elimination, but also because it's just a lot of writing. And so the matrix method saves you a lot of writing. It's one advantage. Now, you can go a little further. It is possible, rather than rewriting the system at this stage, right, going from here and saying, okay, I'm going to rewrite the system, You can go a little bit further and put this into reduced row echelon form where these are zeros and these are zeros. So let me come back here. And at that star stage, we could continue row ups to put into reduced row echelon form. And I want to show you what that looks like. So at that step star there, we said, okay, I'm in row echelon form. So my corresponding system is upper triangular. So I can rewrite the system and solve it very easily by back substituting. If for whatever reason we really liked staying in matrix land, didn't want to go back to systems land, didn't want to rewrite it like this, just wanted to keep working with matrices, we can. There's a way to avoid all this. That's what I'm saying. There's a way to get to the answer working purely with matrices. Let me show you that now. I'm going to cover up the bottom half of this page. And we're going to get that same solution by continuing to work with matrices. All right. Remember what reduced row echelon form says? It says that the first entry in each row needs to be non-zero. Above and below each of the first entries in each row needs to be zeros. So okay, below each entry in each, below the first non-zero entry in each row right now I have zeros, but I need to clear out the stuff above. So in here, I'd want to kill this 2. Over here, I'd want to kill the 4 and the -1. And the way you kind of do it is you work your way back from right to left. So next, I want to kill the 4 here and the 1 here. Sorry, -1 here. So the way to kill the 4 would be to say, okay, my new row 2 is going to be my old row 2 minus 4 copies of my old row 3. Rows 1 and 3 don't change, so I'll copy them down. 1, 2, 0, 0, 2. If I multiply, the reason you do this last is because these are both zeros now, so they won't mess up this stuff. So -4 times 0 plus 0 is still 0. -4 times 0 plus 1 is still 1. -4 times 1 is -4 plus 4 is now 0. -4 times -2 is +8. +8 plus -7 is +1. First step, going further. Next, I would want to kill this -1 over here. That guy is an element of row 1. And all I have to do is add this to that. So my new row 1 is going to be my old row 1 plus old row 3. Rows 2 and 3 don't change here, so I'll copy them down. 0, 0, 1, -2. 0, 1, 0, 1. Now, 0 plus 1 is still 1. 0 plus 2 is still 2. 1 plus -1 is now 0. And -2 plus +1. Yeah, just adding, right? -2 plus +1 is -1. So we're just clearing out more entries of the matrix. So now I've got zeros above this guy. I come back to this guy. I've got zeros below him. I need zeros above here too. So how do I make this 2 into a 0? I multiply row 2 by -2 and add it to row 1. So my next row up be to say my new row 1 is going to be my old row 1 minus 2 copies of my old row 2. Rows 3 and 2 don't change here. Now, row 1, what's going to happen here? Well, I'm multiplying row 2 by -2 and adding it to row 1. So -2 times this plus this is still 1. -2 times this plus this is 0. -2 times this plus this is 0. -2 times this plus this is -3. Do you see the beauty of this? So a few more row operations. Of course, we can combine several of these into one step like we did earlier. What are these numbers on the right?
The coordinates.
It's the solution. Yeah, it's the coordinates of the solution. -3, 1, -2. Solution is the ordered triple -3, 1, -2. And that's not a coincidence because you can think of this as the system of equations. X equals, right? This is X plus 0y plus 0z equals -3. 0x plus y plus 0z equals 1. And 0x plus 0y plus 1z equals -2. So because we've made all the other coefficients 0, you can literally just read off the solution now. That's why people like reduced row echelon form. It's got a lot of convenience. In certain settings, also, you guys don't have a TI-84, but the TI-84 actually has an RREF function. So you input the augmented matrix, tell it, put this in reduced row echelon form, and then you can just read off the system on the right-hand side. Computers are very good at this. Okay. So that's how we do it. That's how we do it. It's not too bad. It's up to you whether you want to stop here, right? Once you hit the regular row echelon form, then you write down your system and back substitute. That's usually, I'll be honest, that's usually what I do. But in some settings, it's nicer to do this, and you need to know how to do both. It's not like it's any harder. It's more of the same shit here. You're just kind of clearing out the stuff above your first non-zero entries, using exactly the same techniques you use to clear out the stuff below them. Okay, so remember last time we saw there are systems with no solutions. There are systems with infinitely many solutions, and I'd like to show you what those can look like. So a system with no solutions, so recall, these systems can have either a unique solution, like the one above, no solution. I want to show you what that looks like in this matrix form. If you're going through this process and at some point your matrix looks like this, then boom, no solution. Your system may have infinitely many solutions. And I bet you guys can kind of predict what each of those would look like by thinking about what the corresponding system looks like. You guys remember when working row reducing the system, how you could tell you had no solutions? What did that look like in terms of like the XYZ system stuff, the stuff like this?
Did they have the same signs?
Well, it wasn't about signs. It was remember we had a contradiction. And so you'd get something like 0x plus 0y plus 0z equals 5. If you had all zeros over here and something that's not 0 here, that's impossible, right? There is no way for 0x plus 0y plus 0z to equal 5 because 0x plus 0y plus 0z is always 0. So a system with a unique solution, that's going to be, the corresponding matrix is going to look like this. Let me show you in general. So unique solution. The matrix here is going to reduce to something like 1, 6, just an example, 1, 3, 0, 1, 2, negative 2, 0, 0, 8. So as you're working through with your row operations, you're able to get into that, row echelon form. And then you say, oh, okay, z equals 8. And then you back substitute that into, y plus 2z equals negative 2 to get y. You'd back substitute that into x plus 6y minus z equals 3. I want you to pay careful attention to the bottom row, especially. Okay. No solution. The augmented coefficient matrix for a system with no solution is going to look something like this. Maybe 1, 2, 5, 7, 0, 1, 3, 4, and then 0, 0, 0, 2, something like that. And one of the reasons I like to draw in that augment bar is to kind of help me see, where everything is. This bottom equation right here would say 0x plus 0y plus 0z equals 2. Super duper not possible. So if these are all 0, everything to the left of the augment bar are all 0. And this is not 0. That's a contradiction. So you've got no solution. And then finally, the infinitely many solution case. There, your matrix might look something like 1, 2, negative 3, 1, 0, 1, 5, negative 2, and then 0, 0, 0, 0. So all zeros on the left and a 0 on the right. I know, you gotta get done. So this bottom equation here, the row, the equation that's represented by the bottom row would be a tautology. Remember, not like this was a contradiction, 0x plus 0y plus 0z equals 2. And this guy is 0x plus 0y plus 0z equals 0. That would be the opposite of a contradiction, a tautology. So in this situation, you would do the same thing we did with the system. We go back and rewrite it. Cute cat. Sorry. It's not a cat. She's a terrorist. She's very cute. She is. She's stay out of the way today.
Oh, that was some good therapy.
Yeah, she's nice. She's nice. Okay. So here, if you've got all zeros here and 0 here, the bottom row, all zeros, then you've got infinitely many solutions. Now I want to take this example that we have here and actually remind you how to express those infinitely many solutions. And to do that, I would go back and say, so in the example above, You know, if there's a unique solution, we know what to do. You just back substitute, find the solution. In the no solution case, you're done. There's no solution, there's no solution. I call it a day. But if there's infinitely many solutions, you're not ready to call it a day. You need to characterize them, right? Like we did in the 2x2s, where I said, okay, yeah, there are infinitely many solutions. That doesn't mean every point is a solution, right? The two lines sitting on top of each other, you can take a point that's not on the line, and that won't be a solution. So how do we write a solution set by letting, so this bottom row, right? The first column, we put it this way, the first column represents x's, the second column represents y's, and the third column represents z's. In the second column, I've got a 1 right here representing 1y plus 5z equals -2. In the first row, I've got a 1 here representing 1x plus 2y minus 3z equals 1. There is no 1 representing a z. There's no pivot in the third column. So that tells me that you're going to let that variable be equal to t. And then solve for y and x in terms of t. And especially if you want to go on and understand the sort of deeper mathematics that underlies this stuff called linear algebra, it's very important to get comfy with doing this. It's one of the big steps between the previous math class and this math class. The previous math class, infinitely many solutions, I give up, is, you know, a C answer. Here, infinitely many solutions, I give up is like a D- answer. You really got to be able to tell me what those are. So we say, all right, I've got the following equations. X plus 2y minus 3z equals 1. Y plus 5z equals -2. And then instead of saying 0x plus 0y plus 0z equals 0, I'm just going to say z equals t. All right. It's a free variable. So backs up. Into equation 2. You get y plus 5t equals -2, which means y is equal to -2 minus 5t. And then backs up both of those into equation 1. So you've got x plus 2y, which is 2 times -2 minus 5t, according to what we just did. No, Edie. Oh, baby, I love you. She gotta get here. Kids are trying to learn linear algebra. So I'm back substituting z equals t and y equals -2 minus 5t into equation 1. So x plus 2y, okay, y is -2 minus 5t, minus 3z, okay, well, z is t, equals 1. And then solve for x. So I guess I'll distribute here x minus 4 minus 10t minus 3t equals 1. So then I add everything over. X is going to be 1 plus 4 is 5. And then -10t minus 3t is -13t. So it'll be plus 13t when I add it over. And I'll pause for a second, make sure you get it clear. So z is t. Y I solve for in terms of that by back substituting. And then x I back sub both of those to solve for. Hence, our solution is any ordered triple of the form x 5 plus 13t, y 2 minus 5t, and z, which which is t, where t is any. And you can write that in the set builder notation, or you can just give it to me like this, it's fine. But I need you to be able to arrive at this ordered triple in terms of the free variable t.
And what's the point of substituting t again? Or what's the point using t?
Well, t is meant to be a parameter, a free variable. So remember kind of the geometry here. In the 2x2 case, when we had a system with infinitely many solutions, what it meant was that the two lines were really the same line. So like any point on that line would be a solution. This. These are all solutions. The system. But a point off the line was not a solution. So there's infinitely many solutions, but you have to be able to tell me kind of what they are. And in that case, you had ordered pairs of like, t comma 2 minus t, something like that. Here in the higher dimensional case, you have an ordered triple. So you're describing all the points in 3D space that are common to the three planes, because those three planes intersected along a line. A line, in other words, in 3D space is something that looks like this. You could just say z equals z instead of saying z equals t, and then this would be 2 minus 5z and 5 plus 13z. And you could write this as 5 plus 13z, negative 2 minus 5z, comma z. But z you usually think of as a variable you're trying to solve for. So the fact that we encountered all zeros in that last row, in this last row, in particular, that there was no pivot for z, right? Like the 1 here is the x, the 1 here is the y. There's no 1 here for the z, and there's no way to get a 1 there for the z because it's all zeros. I can't make a 1 show up. Tells me that the z variable is not determined by this system, meaning the system of equations described three planes that intersected not at a point, but in a line. So if you tell me what z is, I can tell you what x and y are. But there is no unique ordered triple that's on those three planes. So if you want to describe that solution set, you need a free variable, right? Because a line is not just a single point, it's infinitely many points. So for every real number t, you get a new solution. Plug in t equals 0, you get a new solution. Plug in t equals 5, you get a new solution. And this is just how we write down all of those solutions in one space. Is that satisfying the itch there, or is it? Are we still not quite?
Yeah, it does. I just didn't understand why we were doing it, but now I understand why.
Okay. The truth is, there's a bunch of different ways to think about this stuff. Okay. In terms of these things called linear operators, what we've discovered is that the kernel of this linear operator is non-trivial. And that's a weird thing. I don't have the language yet we don't have the language yet for me to describe all that to you. But you can think of matrices as functions, really. That's what matrices are, they're functions. And this is a function that kind of sends multiple different vectors to the 0 vector. That's what it means to say the kernel is non-trivial. And what this does is it measures the dimension of the kernel. Those are all things you can tell people if you want to scare them a little bit. But if you want to know really the depth there, I suggest taking a course called Linear Algebra. It's a wonderful course. So that's it. This is how you solve systems of equations using matrices. The real heady stuff comes from abstracting from here, which is getting closer to what I was just talking about, thinking of matrices as functions rather than as these tools for describing systems. So if you guys are genuinely comfortable with where this ordered triple comes from, I'm going to start discussing the algebra of matrices. Are there any other questions about how we got here or the row operations on matrices? Okay, here we go. This is section 10.4. I'm going to teach you guys how to add matrices, subtract matrices, multiply, and even kind of get close to dividing matrices. One of the things you'll discover as you go further and further in mathematics is that the word algebra doesn't mean what high school students think it means. The word algebra means a set with some structure. Objects that can interact with each other through rules. You know, that's it. That's what algebra means. It's got nothing to do with X, Y, and Z. It's all about having some objects that are capable of messing around with each other according to some rules. Specifically in algebra is a set with some rules that forms a particular structure called a ring, where you can add two things together and get another one like that. You can multiply two things and get another one like that. Matrices form what's literally called an algebra, which is a special kind of ring. So two matrices of equal dimension are equal to one another if they have all the same entries. In other words, you know, the more strict way of saying this is if A is the matrix whose entries are Aij, and she is an M by N matrix. This is just notation. This means the matrix A has entries Aij and is an M by N matrix, M rows, N columns, and B is also an M by N matrix whose entries are Bij, then if this and this, then A equals B if and only if the Aij entries are equal to the Bij entries for each 0 less than or equal to I less than or equal to M and 0 less than or equal to J less than or equal to N. This is kind of abstract looking, right? Looks a little scary. But what I mean by this is compare two matrices. If you sit them on top of each other and every entry is identical, then we call those matrices equal. Let A be the matrix, the 2 by 2 matrix, A, B, C, D, and B be the 2 by 2 matrix, -1, 3, 5, 2. Then A equals B means little a has to be -1, little b has to be 3, little c has to be 5, and little d has to be 2. Right. For this matrix to be equal to this matrix, the 1-1 match, 1-1 entries have to match. The 2-1 entries have to match. Right. I need A21 to be equal to B21. That's kind of what we're saying here. I need A22 to be equal to B22. Another example of two matrices that are equivalent. Another way to write these also, I could say that the matrix square root of 4, 2 squared, e to the 0, 0.5, 1, and 0 cubed is equal to the matrix 2, 4, 1, 1/2, 1, 0. Why? Because the square root of 4 is 2. 2 squared is 4. E to the 0 is 1. 0.5 is 1/2. 1 is 1, and 0 cubed is 0. Seems stupid, right? Seems like duh. But you know, equality, we got to define it. We don't, matrices aren't numbers. So if I'm going to say two matrices are equal to each other, I have to tell you what that even means. All right, so one of the kind of silliest things I could do is just ask you, here's a matrix, are these equal? An important thing, they have to have the same dimension. They have to have the same dimension, and the entries have to match up term-wise. So like, 2, 0, 1, 3 is not equal to 0, 2, 1, 3. These definitely aren't the same. Even though they're both 2 by 2s and they have the same entries, they're not in the right place. All right, 2 is not equal to 0. 0 is not equal to 1, blah, blah, blah. Another thing, even if everything kind of lines up, okay, so here's two matrices which are also not equal. This is a 2 by 3 matrix. This is a 3 by 2 matrix. So they can't be equal. They don't have the same dimension. They have no way for them to possibly be equal. How do we feel about these? Let's start back here. Any questions about the first example? Questions about the second? The third? And the fourth? So for two matrices to be equal, they gotta have the same dimension and they have to have the exact same entries in the exact same place. That's what it means to say two matrices are equal. Next. Adding, subtracting, and multiplying a matrix by a number. So the term for multiplying by a number, by the way, is scalar multiplication. That word scalar should look familiar. We used that word when we talked about transformations. Remember? Vertical scaling, horizontal scaling. Scaling means to multiply by a number. So if A is an n by n matrix, B is an m by n matrix, so A and B are matrices, both of the same dimension. Then A plus B is an m by n matrix, formed by adding the entries. component-wise. Meaning I take the 1, 1 entry of A and the 1, 1 entry of B and I add them. I take the 1, 2 entry of A, the 1, 2 entry of B and I add them. For example, 1, 0, 2, 0, 1, 3, 1, pi, -2. I can add 2, 0, 1, -3, 2, 0, 5, -6, 2 pi, 1. If I add these together, they're both 3 by 3s, so I'll get a new 3 by 3. The 1, 1 entry of the result is 1 plus 0, which is 1. The 1, 2 entry of the result is 0 plus 1, which is 1. The 1, 3 entry is 2 plus -3, which is -1. 0 plus 2 is 2. 1 plus 0 is 1. 3 plus 5 is 8. 1 plus -6 is -5. Pi plus 2 pi is 3 pi. And -2 plus 1 is -1. Just add up the entries component-wise, one bit at a time. Differences work the same way. Okay, subtraction. All right, so if you want to subtract two matrices of the same size, like 1, 0, 2, and -1, 1, 7, and I'm going to subtract that. I'm going to subtract from that the matrix 3, 0, 5, 2, -2, 1. The result would be a new matrix of the same size. Whose 1, 1 entry is 1 minus 3, which is -2. 1, 2 entry is 0 minus 0, which is 0. 1, 3 entry is 2 minus 5, is -3. -1 minus 2 is -3. 1 minus -2 is +3. And 7 minus 1 is 6. Component-wise. Multiplying by a number this is actually the first place where you have to think like a little bit about how you would do that. So do I multiply just one entry of the matrix by that number? Do I multiply one row of the matrix by that number? Do I multiply every entry of the matrix by that number? Turns out it's the last guy. So if A equals Aij is an M by N matrix, and C is a number, then CA, a constant or a number times that matrix, you multiply every single entry. So that would be CA ij should be another M by N matrix. Multiply every entry by the number. So for example, if I have the matrix 2, -3, 0, 5, 7, and 1/2, and I want to multiply it by 2, the size of this matrix will be the size of the result dimension, and then you just multiply every single entry. So 2 times 2 is 4, -3 times 2 is -6, 0 times 2 is 0, 5 times 2 is 10, 7 times 2 is 14, and 1/2 times 2 is 1. Those are your 3 easy operations: scalar multiplication, subtraction, and addition. You might ask, why am I not telling you how to multiply matrices here? Well, the answer is because matrix multiplication, multiplying a matrix times a matrix, a little bit more complicated than you would think. First thought, just multiply them component-wise. That's what we did for addition and subtraction. It works great. Nah. And for very good reasons, nah. Remember what I said, matrices are actually functions. And we want matrix multiplication to be the same thing as function composition. Now it's a little more than I can really justify to you right now, but I can show you the rule. And you will need to use the rule. And it will become clear why the rule is the way it is after I've shown you how to divide matrices. Namely, how you can use matrix multiplication, kind of division, to solve systems. Now, some properties, I guess, before I show you multiplication in general. Facts. If A and B are n by n matrices, the following are always true. 1. A plus B is the same as B plus A. You might think this is obvious, it's not. I mean, it kind of is, but we're defining a new operation. We're adding matrices here, not numbers. And we had to define what it means to add two matrices. Maybe our definition of addition for matrices was such that it's not commutative, but it is. Addition of matrices is commutative. It's also associative. Remember what that means? That means if you take A and add that to the sum of B plus C, I should say A, B, and C. So A, B, and C are all matrices. That's the same as taking A plus B and adding that to C. Addition is commutative and associative. It's good. Scalar multiplication also plays nice. I skipped 2. 1, 2, 3. Scalar multiplication is pretty nice. So if C and D are numbers, then C times the matrix DA is the same as CD times the matrix A. So if you take your matrix, multiply by a number, that'll give you a new matrix. If you then multiply that matrix by another number, it's the same as multiplying the two numbers and then multiplying the matrix by that. We also have a distributive property. C plus D times the matrix A is CA plus DA. And you have kind of other sort of distributivity. C times the matrix A plus B is the same as C times the matrix A plus C times the matrix B. So matrix addition is commutative, associative. Scalar multiplication is associative and distributive. Good news. Good news. All right. I'm going to give you some basic homework problems where you have to kind of solve silly little matrix equations. I don't have time to show you how matrix multiplication works today. So let me show you one of those. The next thing we're going to do tomorrow, talk about how to multiply two matrices, A times B. It's not what you think. It's weird. It's weirder, even though I'm telling you it's weird, it's going to be weirder than you're thinking still. The matrices have to be of different dimensions, or it can be of different dimensions. The resulting matrix is different dimensions, potentially. You can't multiply any two matrices. They have to have like the right size, and it's not commutative. A times B is not the same as B times A, even in the nicest possible cases. So I'm going to save that for next time. It's too much to do right now. But let's solve. So for example, let's solve the matrix equation two times capital X here, so a big X, minus A equals B, where A is a 2 by 2 matrix whose entries are 2, 3, -5, and 1. And B is a 2 by 2 matrix whose entries are 4, -1, 1, and 3. So first, can anybody tell me, that's the whole problem. Can anybody tell me the dimension of the matrix X? If X is a matrix that solves this matrix equation, how many rows and columns does X have to have?
2 by 2.
Gotta be a 2 by 2, right? Gotta be a 2 by 2. If A and B are 2 by 2s, X is built up out of, this equation involving 2 by 2 matrices, and none of these operations change dimension. So X has to be a 2 by 2. All right. The rules above tell me I can do the following things. Two X has to be equal to B plus A. I can add A to both sides. All right. I take this matrix equation and I add A to both sides, and I think about doing it on the right. To get rid of this minus A, I'm going to add A. So that, just like with numbers, works fine. And then I can divide both sides by 2, except we haven't really talked about dividing a matrix by a number. So I'm going to write it as multiply both sides by 1/2. And I get X equals 1/2 parentheses B plus A. Divide by 2, multiply by 1/2, same thing. Now, that's 1/2 times the matrix B, which is 4, -1, 1, 3, plus the matrix A, which is 2, 3, -5, 1, which is 1/2 times, now we'll simplify inside here. The matrix B plus A, this is 4 plus 2, that's 6. -1 plus 3, that's 2. 1 plus -5, that's -4. And 3 plus 1 is +4. And if you multiply that matrix by the number 1/2, that means you multiply every entry in that matrix by the number 1/2. So the 6 becomes 3, 2 becomes 1, -4 becomes -2, +4 becomes +2. So the matrix X that solves this equation is 3, 1, -2, 2. All right, this is your very gentle introduction to matrix algebra. Like I said, next time we're going to talk about matrix multiplication, which is substantially more complicated. So I strongly encourage you to work some of the homework problems before coming back. I'm pretty sure I've published both of your last homework sets already. Let me take a look here and make sure. I did for my differential equations class, I'm not sure. Publishing these yet. If not, I'll go ahead and publish them right now. In here. Yeah, 8 and 9 are here. So if you look in here. Come on. Right, that's still log stuff. Okay, log and exponential equations, that's stuff we learned last week. Right, so this is going to be all system stuff. Probably no matrices yet, right? Yeah, just systems. Okay, nope. So I still need to publish your next homework sets. You're going to have 2 more homework sets. So homework 10 is going to be on matrices, this type stuff, but also stuff with multiplication of matrices. And then homework 11, which I'll probably publish after class on Thursday, you'll be able to work on it until the final. Something like that will be on sequences and series. So I'll get in here right now and publish your next homework set, which is going to be on the algebra of matrices and kind of converting systems to matrices, solving all that good stuff. I want you to get started on that as soon as you can. So these guys, we want to be crunching through 8 and 9. We want to be close to done with these by today. And I would like you to take a look at least at homework 10 before class tomorrow, if at all possible. Alrighty, gang, that's it for today. I hope you have a good rest of your day. If you need anything, you can come see me in office hours. I do have an office hour from 3 to 4 today. Otherwise, I will see you tomorrow when we will explore more of the algebra of matrices. And you'll finally see what I mean when I say matrices are functions, which is pretty big, pretty cool stuff. But that's it. Until then, I hope you guys take good care of yourselves. If you need anything, just let me know. See you tomorrow.
And
See you
man,
tomorrow.